Hello all, this is Dr.C.Padmini taking a lecture on electronic devices and circuits, and today's lecture is lecture 3, and today's topic which we are going to cover is nothing but diode resistances and capacitances. Under different biasing condition, what are the resistance, amount of resistance exhibited, what are the types of resistance exhibited, as well as the capacitance we are going to study. And in the previous class, as we have just seen, the operating condition of a PN junction diode we have just seen when it is applied with a forward bias, how the conduction is, current equation, diode current equation. Along with this, we have also seen the effect of temperature onto this forward and reverse bias condition also we have just checked. So today it's a continuation of it. What are the properties of resistance and capacitances exhibited by the PN junction diode under different biasing conditions we are going to check in. So let us start this topic today. And first we can just go on with the PN junction diode. As we all know, it's a P and N combination forming a junction, and it's a device which is operated under forward bias and reverse bias. So under forward bias, as we have seen, till the barrier potential, the conduction is almost zero. After barrier potentials, the majority carriers cross the junction and current will be constituted. And later, under reverse bias condition, the current is only because of the minority carriers. Till a breakdown voltage, you see that as we increase the reverse voltage, the reverse current also increases. But once the breakdown voltage is applied, because of the avalanche multiplication, the carrier concentration increases. And also suddenly there will be a drastic rise in the reverse saturation current as well. So today we are going to study about this concept of diode resistances, the amount of resistance offered by a diode under different conditions. That is, when we apply a forward bias and when we apply a reverse bias, what are the properties exhibited. So let us start up with this. Broadly we just try to classify this diode resistances in this manner. First we are going to define them based on the type of signal that is applied. We have the classification done. That is, whether you want to study this resistance property for a static voltage that has been applied. As an example, if I am applying a DC signal onto a PN junction diode, what is the resistance offered? We call this DC resistance, we call it as DC resistance, and it is also called as static resistance. And if I am applying an AC signal onto a PN junction diode, how the resistance offered is, that is defined as a dynamic resistance. As the signal is getting altered, we are going to define. So firstly we are going to speak about it, the classification. All right. First we classify it as a static resistance. Okay. The second one is dynamic resistance. And this resistances we are going to define it. Static resistance is also called as DC resistance, and dynamic resistance is also called as an AC resistance. All right. Further, depending on the biasing that we apply, we classify them to be as the further classification done under forward bias condition as forward resistance. Under forward resistance condition, we are going to analyze both the things, that is your static and dynamic, as well as when we apply a reverse bias to the device, what is the resistance offered, we are going to analyze it. So we have altogether 4 different resistances which we are going to analyze, that is your static resistance and dynamic resistance under forward bias condition, and static and dynamic resistance under reverse bias condition. So let us start up with a forward bias condition. This is a resistance that is offered when the PN junction is applied with a forward bias. As we all know that the diode, when it is applied with a forward bias, it implies that your P material is connected to positive terminal of the battery and N material connected to negative terminal of the battery. This is the input applied, and the series arm resistance for a protection purpose, this is my diode. So when this forward bias has been applied, as we all know that it offers almost till a barrier potential, that is V gamma. Till the V gamma, the current was very small, which implies that the current resistance offered is very high, and as we try to go for V gamma and above to it, the current has got raised in the range of milliamperes, which implies the resistance reduces. So let us analyze the static and dynamic resistance by taking your forward characteristics. Forward characteristics is plotted between forward voltage and the forward current. which will be in the range of milliamperes as we have analyzed in the last class. We have the characteristics in this manner, almost a zero current till a V gamma potential. Once barrier becomes zero, we see that at V gamma the conduction gets started. That is, majority carrier starts moving from the junction. So respectively we are going to have the majority carrier current constituted. So here when we want to define a static resistance, that is nothing but the DC resistance of a device we call it. So DC resistance we are going to define it in this manner. Under forward bias condition, I am trying to define my DC resistance. DC resistance is static resistance, which we also call it as DC resistance. Okay. And as we know, DC is a constant voltage that has been applied. So your resistance under forward bias condition, so I am calling it as RF, and this is simply a ratio of forward bias condition we are taking. So forward voltage, as per the Ohm's law, we have a relation that V by I, forward resistance versus forward current, ratio of it. And from the characteristic curve, if at all we want to define the same, we can just define it by identifying any one point after the conduction gets started. After V gamma, we just try to identify one point, and that particular point has been taken up and extended it. That point is extended onto your x-axis, right, onto your y-axis, which will try to define your forward voltage at that instant of time and respectively the forward current. The ratio of at a node A or some point called A has been identified, and at that instant whatever the voltage to that of its current, the ratio when it is taken, it will be Vf by If, which defines your static resistance. And as we know, as it is conducting, majority carrier current is present, this particular forward resistance will be in the range of few ohms. Few ohms will be exhibited, some around 25 ohms to at most of 800, 900 ohms you are going to get it under forward bias condition. Similarly, we have a dynamic resistance present. Dynamic resistance, we are going to define it as also as a AC resistance. When a time changing signal is applied, what are the property of resistance? What is the amount of resistance offered by the device? We call it as AC resistance. So in order to define this AC resistance, we are going to take up our characteristics in this manner. From the characteristics, if at all we want to plot, we are going to identify two different points on the graph and extend these 2 points as already taken as A, take it B and C. Just extend the 2 points onto your x-axis as well as y-axis. Alright, node B or point B and point C. So try to take the difference between the two voltages, which we call it as delta Vf, right, under forward bias condition, and the difference of the current we shall just try to take it, which is going to be your delta If. Alright, your dynamic resistance, which we represented with the small letters, time changing parameter, Rf is equal to delta Vf by delta If, or otherwise we also write it as dVf by dIf. Okay. So this is how we define the dynamic resistance of a PN junction diode under forward bias condition. And in order to define this value of it, or in terms of the numerical, we can also define this dynamic resistance by taking a diode current equation, as we have discussed in the last class. We have a diode current equation defined to be as I is equal to I naught into e to the power of V by eta Vt minus 1. Right, differentiate this equation with respect to the voltage V and find out, take inverse of it, that will give us the dynamic resistance. That is, your forward resistance is going to be dV by di. In order to do this, we shall just try to take the current I equation. We will be just taking it, with the help of which differentiate it with respect to V and take an inverse of it, that gives your dynamic resistance. Taking a inverse of it and deriving, you are going to get a dynamic resistance of your PN junction diode to be as eta Vt by I. By analyzing it, we are going to take, and here we are going to make one more assumption that this current, when it is further analyzed, you are going to have this I is equal to I naught into e to the power of v by eta vt. So, this particular point we can, when we elaborate it, the same equation I am trying to rewrite, I naught e to the power of v by eta vt minus 1 into I naught will become I naught. Alright. So, keenly observing the equation, this is the forward current which will be in the range of milliamperes. Alright, and I naught is nothing but your reverse saturation current. Reverse saturation current is maximum current that flows under reverse bias condition, which is in the range of microamperes. So, keenly observing the equation, I is equal to I naught e to the power of v by eta vt minus I naught, and I is in the range of milli and I naught is in the range of microamperes, which implies that your majority carrier will be approximately equal to that of this. This factor is going to be milliampere, which derive your total current to be in the range of milli. So, because of which we can also in this derivation of your dynamic resistance, we are going to make an assumption that this current is approximately taken to be this, by which we are going to make a substitution over here. So, the dynamic resistance of a PN junction diode is equal to RF is equal to eta Vt by I, and from the graph we can just derive it by identifying 2 points after V gamma. Just extend the 2 points onto your x and y axis, which gives you the change in the voltage with respect to it, the current change also, delta IF we are going to find it, and take a ratio of them, that gives our dynamic resistance. Alright, this is how the forward resistance can be derived, by taking a diode to be under forward bias, and both the resistance will be in the range of few ohms. Since the device is under forward bias, the current is because of the majority carriers. So, the resistance will be very low comparatively. So, it will be in the range of few ohms. This is how forward resistance is. Similarly, we have a reverse resistance also taken up. So, simply take your PN junction diode, apply a reverse bias to it, and let us see how does the resistance would be. P material connected with a negative terminal of battery, N material connected to positive terminal of the battery. This is my input voltage with a resistance. I am trying to connect a diode D. So, this is your reverse bias condition of a PN junction diode. As we know that under reverse bias condition, the current is only because of the minority carriers. As there is a barrier present, the majority carriers cannot cross the junction. So, respectively, it cannot have the conduction of large value, very small amount of current is flowing through the device. So, because of which the reverse resistance offered will be comparatively large. In terms of few kilo ohms we are going to get it. And here also again, depending on the AC or DC condition in which you are using your diode, according to which we have the resistance is defined to be as static resistance under reverse bias condition. Right, static resistance we also call it as DC resistance. Here also the same, your static resistance under reverse bias condition, it is simply a ratio of VR by IR. In order to derive this, we can take our reverse bias condition. Right. Let us plot the graph reverse. It will be in the third quadrant. This is your reverse saturation or reverse current, microamperes or nanoamperes it will be, and this is your reverse voltage V. Alright. So, the curve how it is present, it is going to start from the origin, slightly increases as we increase the reverse bias, and till breakdown. Once the breakdown occurs, the current increases drastically. We are going to represent this as VBD, breakdown voltage. Alright, this is the curve that we have. With the help of the curve, that is before breakdown, we are going to consider the device in order to define its resistance. So, identify any one point on this graph, that particular point we are going to take it as the element to find out your static resistance. So, assume a node A has been taken up. Try to extend your current and onto your x and y axis, which will give you your reverse voltage and reverse current. So taking a ratio of this VR by IR, that will give you your reverse resistance. As we all know, it is under reverse bias condition, current is very small. The resistance offered by this device will be in the range of few kilo ohms, we will be getting it. So similarly, we can define our dynamic resistance as well. Dynamic resistance is also called as DC resistance. Alright, sorry, it's an AC resistance. Alright, so we are going to find out in the similar manner, identifying any 2 points on the curve, extending them onto your x and y axis, node B and C, right? Extending them onto your x and y axis. Y axis difference would be delta IR, and x axis between node and A, B and C is going to be delta VR. The ratio of these things will be defining your reverse resistance, delta VR by delta IR. Okay, or otherwise the same can be written as dVR by dVi. Okay. So this is how we try to find out the dynamic resistance. This will also be in the range of few kilo ohms. Under reverse bias condition, current is in the range of micro. The ratio would give you a resistance in the range of few kilo ohms. So this is how we have the resistance offered by a PN junction diode under forward bias and under reverse bias condition. And next we shall just try to go for a concept of diode capacitances. This property is the one which depends what kind of a biasing that you apply, according to which we have the different type of capacitances exhibited. So broadly the diode capacitances are classified into two types. One is called as transition capacitance, as you can see it in the slide. It's the transition capacitance, which we represent it to be as CT, and second one is diffusion capacitance. Transition capacitance and diffusion capacitance. And transition capacitance is the one because of the transition region, or we also call it as depletion layer. Depletion region, we have a capacitance. So depletion layer is present under reverse bias condition, whereas under forward bias it decreases and it vanishes as well. So transition capacitance is the one which is exhibited under reverse bias. Okay. Diffusion capacitance is because of the charge particles getting diffused from one region to that of another. Particles crosses the junction because of the concentration difference, and that particular process of crossing, during that time there is a capacitance property exhibited, so that we call it as diffusion capacitance, and majority carriers will cross the junction under forward bias condition. So diffusion capacitance is exhibited under forward bias condition. So going on to the details of it, as we all know, transition capacitance, as it is stated, reverse bias condition. So this is my structure diagram. When a PN junction is applied with a reverse bias, right? Applied with a reverse bias, P material connected to negative terminal, N material connected to positive. This is your reverse biased PN junction diode. And as we know that because of the ions which are present, they get accommodated on either sides, negative ions onto P side, right, positive ions onto N side. As we have discussed in the initial stage, the formation of depletion layer, initially as in when a PN junction is formed, the particle tend to go for a recombination. Some around 5% of the particles tend to go for the recombination. So there will be a neutral area that is formed across this P and N that forms your junction. And on either sides of this neutral area, we have an ion accommodation. So it's nothing but you have a neutral area in between which works like a dielectric. On either sides of it, we are going to have a charge accommodated. So this exhibits a property of capacitance, having a negative charge on one side, positive charge with a dielectric in between them. So this particular capacitance, because of the transition region, we also call the depletion layer as transition region. So because of this transition region, a capacitance has been exhibited, so hence we call it as a transition capacitance. As we represented, the transition capacitance is represented by CT, and when it is analyzed by taking the depletion layer into consideration, the equation comes out to be CT is equal to epsilon A by W, where epsilon is the permittivity of the material taken up, A is the cross-sectional area of the device, permittivity of the material, and A is the cross-sectional area, and W is the width of the depletion layer. Depletion layer, which we also call it as transition layer or transition region. Alright, so this is how we have a transition capacitance exhibited, which is because of the depletion layer exhibited. We have applied a input of reverse, which is connected to diode D. Under reverse bias condition, transition capacitance is exhibited, and this is how we have. And you can just see, as you increase the reverse bias, width of the depletion layer increases because of more and more ions getting accommodated. So obviously the capacitance also decreases as the reverse bias is increased. As we increase the reverse bias, width of the depletion layer also increases, which leads to a decrease in the transition capacitance. As you can see, the relation, inverse relation, CT is equal to epsilon A by W. So this is the transition capacitance exhibited by the PN junction diode when it is under reverse bias condition. Similarly, under forward bias condition also we have a diffusion capacitance exhibited. So let us take our PN junction diode and apply a forward bias and check for this diffusion capacitance. Okay. This is how P material applied with positive terminal of the battery, N material with negative. This is the input voltage that I apply through a resistor to a diode D. Right, assume that my input applied is more than to that of barrier. Before to it there was a depletion layer will be present, because of which majority carriers will not cross the junction. So apply a condition that your Vi is greater than the barrier potential V gamma, or Vt, various notations that we use it for the threshold voltage, or we call it as barrier potential. So if it is applied more than V gamma, depletion layer completely gets nullified, because of which you don't find any depletion layer. So majority carriers which are present in P are nothing but your holes will tend to move, because of, as we have discussed in the last class, particles can move because of the two reasons, diffusion as well as drift, because of the concentration difference. In N material we have electrons to be the majority carriers, in P material we have the holes to be the majority carriers. So since the depletion layer has got vanished, the holes can move from P to N and electrons can move from N to P. So majority carriers start moving from one region to the other because of two reasons. One is the diffusion, the other is drift. Diffusion implies, as we all know the definition of it, the migration of particles from the region of higher concentration to the region of lower concentration. So the particles are moving, hole is moving, entering into N material. As and when hole enters into the N material, what will happen? They become the minority carriers. So then there is no more concentration difference that is present. They have entered into the least concentrated area. So they cannot diffuse further, but because of the force acting from the battery, because of the drift, the particles will move. So because of this diffusion concept, we see that the holes which are moving from P to N will travel certain distance with a drift velocity, with certain velocity. As and when they enter into the other region, they become the minority carriers. So they no more go for a diffusion process, they just go for the, because of the drift, the particles will move, which implies that at any instant of time it is taken up, holes from the P material tend to move through into N, and as the velocity suddenly reduces, we find that there will be, after certain distance, we find that holes are stated to be accommodated. They are just moving on from one region to that of another, they just diffusion concept gets completed since they have entered into the lower concentration region, and because of the drift the particle tend to move, which implies that the velocity with which the particles move from here to here will be different from that of this movement, which implies that they rush because of drift and diffusion from one region to that of another. Once they enter into n material after certain length that has been traveled, which we call it as diffusion length ln, as they travel in n material we call it as ln, in the p material we call it as l. This is l p for the holes that have been. So this, after traveling this distance, the particle tend to move with a different velocity. So it appears that the ions charges which are moving from p to n, that is holes which are getting moved from p to n, appears to get stagnated at one particular point. They are not static over there, but they take the velocity gets altered at this instant, because of which slowly they start moving because the diffusion concept is over. So we see that we find that at a particular length of ln and lp, respectively we have electrons getting accommodated on the other side, which are moving from n region to that of p. So with that distance of ln they travel, lp on the other side, hole length, diffusion length and electron. So they travel certain distance, the velocity suddenly reduces, they move on with a drift velocity. So because of which we see that whole charges will be dominated at one particular length, and negative charges, that is electron charge, gets dominated after certain traveling certain distance. So this try to form your capacitance property, that from the junction on either sides, onto n side you see positive charges, holes are stated to be accommodated, they are just moving from p to n for a fraction of minute. It is stated to be retarded, but with the drift velocity they again continue to move. So continuously this process happen, one particle moves on, the next one will come and accommodate, which implies that at a certain distance of lp and ln you see that the charges are getting accommodated. They are not static, they are moving, but the next particle is replacing that point. So we find the capacitance property exhibited over here, and this capacitance is exhibited because of the diffusion of charge carriers. So hence we are calling it as diffusion capacitance. Diffusion capacitance CD, as we all know, we can just derive it as dq by dv, depending on the amount of charge that is traveling based on the potential applied. We are going to define this diffusion capacitance. dq by dv is the expression used. So altogether diode exhibits resistances as well as capacitances under forward and reverse bias condition. Static and dynamic resistance we have, and also the capacitances are depending on the biasing. Under forward bias you see the device exhibiting the diffusion capacitance, and under reverse bias it exhibits the transition capacitance. So you see the property of resistance exhibited and also the capacitance exhibited by p-n junction diode. So next we shall just try to see what is the actual practical scenario condition of a p-n junction diode, and what is the ideal condition that we take when we use a diode in any practical application. We assume it to an ideal condition, and practically what is the thing, ideally what we make an assumption, we are going to discuss it over here now. So practical diode, as we know, depending on the bias that we apply, it do offer certain value of resistance, it has a current conduction happening. So based on that we also define the equivalent model of it, ideal condition and under practical condition we are going to take up. So this ideal versus practical, we are going to draw the equivalent model and define what are going to be its resistances and capacitances. So when this is the normal p-n junction diode which I have taken, for which I am going to draw a linear piecewise equivalent model. We call it as piecewise linear model, which will give you a practical diode. This is nothing but your practical diode. Practically when you are using it, a diode in a circuit, what all properties exhibited, that has been defined. As we have seen in the previous topic that it do exhibit certain value of resistance. So diode will have, either it is under forward bias condition or under reverse bias, it exhibits a resistance. So assuming the diode to be under forward bias, I am trying to draw this equivalent circuit. So you have some resistance exhibited by the diode, and along with this it has a barrier potential present, and barrier depending on the polarity of ions that have been accommodated. On p side we have a negative charges getting accommodated, on n side we have positive. To nullify that, we reverse the place the polarity of the supply. So this is your V gamma potential exhibited, and if it is under forward bias, this is going to be your forward resistance, and along with this it always the symbol of the diode defines the direction of current. So this is how the direction of current is. Majority carrier current moves in this direction, minority in the reverse fashion. So this is how a piecewise means all the properties exhibited by p-n junction diode are defined as different pieces. Combinedly we are trying to define a linear model of it, piecewise linear model, which is nothing but your practical diode condition. So which implies that you are considering the resistance offered is not equal to 0, and you are also considering that it has a barrier potential V gamma which is not equal to 0, and we have a diode considering its diode conduction direction. This is your practical diode. Similarly, we have another simplified model also present in between. Simplified model, we are going to consider we can ignore certain parameters by which we can define your simplified model of it, and we are going to use this piecewise linear model whenever you use your diode in practical applications, and if at all you want a practical conditions, not an ideal, practical conditions when you have to analyze, then we are going to replace our diode with its equivalent model and then do the analysis. So simplified model, when we try to plot it, we just try to ignore the resistance. Since forward resistance is in the range of few ohms, we can just simply ignore it and take out the barrier potential along with the diode direction. So this is a simplified model where I am trying to take my forward resistance to be 0. Since it is very small, it is almost taken to be as 0. So this is the diode direction, this is your barrier. This is simplified equivalent model, according to which the VI characteristics also gets altered. So let us plot for the piecewise linear model. As it is practical case, the VI characteristics is going to be the same. This is your forward, and this is your forward current in the range of milliamperes, and reverse bias condition, reverse current, which is in the range of microamperes. So here, as we know that the graph would be till barrier, the current will be 0, almost 0, it will increases and linearly it will rise. After the breakdown, the current suddenly increases. This is your VBD and this is your V gamma. Very small current or almost 0 current we just stated. Since the current will be only because of the minority carriers, almost a 0 current. So this is your equivalent model or graph of your piecewise linear model. But here when we are going for a simplified model, we are ignoring the forward resistance. Resistance when it is equal to 0, so the device will be working like an ideal case. As in when I apply my diode to be with a what we call a forward voltage more than V gamma, the diode will conduct without any resistance. Here when you just try to look at the curve, linearly it is rising, which implies that when you try to relate the voltage to that of current, it offers certain resistance. So ideal simplified model, we are taking the forward resistance to be 0, so the conduction of it will be happening in this manner, or the characteristics will be taken in this manner. So till V gamma, absolutely almost 0 current. The resistance is 0. So as in when you apply your V gamma potential, the current rises linearly. Sudden rise means almost the resistance offered by this particular curve would tend towards 0, which is Vi by I, V by I. Since voltage variation is not much, as in when V gamma is applied, conduction has started, so the resistance tend towards 0. This is your second case, simplified model of the transistor. And practical versus ideal, so we have to define the ideal condition as well. The third diode which we are going to plot it is an ideal diode. In this ideal diode, we ignored your forward resistance, that is as it is very small, it is taken to be, and also we ignored the barrier potential. If at all you are applying a large value of AC signal such as 10 volts or 12 volts, the 0.7 or 0.2 volt of barrier can be ignored. So under that particular condition, we try to ignore these two, forward resistance as well as barrier potential. So ideal diode, we can just draw it in this manner. This is how my ideal diode will be, which implies that it has the maximum current in one direction, in the other direction there is no current. So if I try to plot my VI characteristics under this ideal condition, forward and reverse is going to be in this manner, microamperes. As it is stated, there is no V gamma, so conduction initially gets started, and there is no resistance also offered as well. So under reverse bias, as we know, the resistance tend towards infinity. So the curve, the graph will lie on the x-axis. Resistance offered is 0, no drop of it. So and also V gamma value is 0, so there is no, it doesn't need to go till a value of V gamma. Since V gamma is 0, directly we are going to get conduction get started as and when you apply your forward bias. So your curve will lie on x-axis on the during the reverse bias condition, and it lies on the y-axis during the forward bias condition. So this is how we have an ideal versus practical condition that has been taken up for a p-n junction diode. So today's session or the lecture 3 consists of the three things: diode resistances we have found, static and dynamic. Later we have just analyzed the capacitance property exhibited by diode. Under forward bias, it exhibits the diffusion capacitance because of the diffusion of charge carriers, and under reverse bias it exhibits the transition capacitance, that is because of the transition region or the depletion region. And along with this, we have just compared the usage of the diode when it is practically used, whether it is a practical scenario I have to analyze or an ideal case. As per it, we have defined the ideal versus practical diode equivalent circuit as well as its VI characteristics. So in the next class, we are going to continue this particular topic, and usage of p-n junction diode, we are going to make an analysis. That's all for now. Thank you.